Hi everybody, welcome back. Now we're going to talk about continuous compound interest. So when you're compounding interest, usually you want to specify a specific time interval over which the interest rate will be applied. So either every week, every month, twice a year, every day. Continuous compound interest applies interest to the account the moment after you get the money. So 1 second later, not even 1 second, 1 nanosecond later, interest is being applied to your account. So it's every instant of time, interest is being applied to your account. And you're going to notice with our example here that that's going to increase the amount of money that whoever lent you is going to receive back. So from the consumer's point of view, you really this is going to make them pay a lot more money versus something that's every day or gets compounded once a month, etc. So notice that the formula is slightly different, and notice that all we need for continuous compound interest is the principal, the rate, and the number of years. Notice that the function e, the exponential with e, comes in, because we can actually write 1 plus m over r to the mt can be rewritten in terms of 1 plus 1 over x to the rx here, or I guess 1 over t, x r to the t, and as this goes to t goes to infinity, this will approach the function e to the rt. And that you just kind of have to believe right now. But that's kind of the reason. The book talks about a little bit more detail, so I'll let you read it there. But this is a very calculusly thing, and if you take Calc 1, you'll learn exactly why that works there. But for right now, you should believe that as t goes to infinity, this quantity will approach that quantity. So let's look at an example here. Suppose 4,000 is invested at 11%, so this is our previous example from the last video, but now we're going to compare after 3 years what happens compounded daily versus compounded continuously. So for both problems, we know that P equals 4,000, R again is 0.11, and now part A and B differ in a couple of respects. So if we're compounding daily, so usually in these problems where we're compounding daily, we're not thinking of leap years. We're really thinking of normal years. So this is going to be M equals 365, and so after 3 years, this will be T equals 3. So our formula is A equals 4,000 times 1 plus 0.11 over 365 times 365 times 3. So let's figure out what that amount is. And remember, this is a compound interest formula that we're using right here because it's being computed daily. So there's a set number of time intervals in a year. And when we calculate that out, notice that this is approximately equal to 5,563.60 So in part 2, all we need is the number of time. We don't need to know the number being compounded continuously. It's being done every moment of time. So now this is given by A equals, so the 4,000 E raised to the 0.11 times 3. And so we just run this through our calculator. 4,000 times the exponential function raised to the 0.11 times 3. And that gives us approximately equal to 5,563.87. And notice that the difference is very small right now. But if you look down the road, so let's change this to 10 years. So let's do an example 3 and compare this at t equals 10. So we'll get A equals 4,000 times 1 plus 0.11 over 365 times 365 times 10. So let's figure out this number here. times 1 plus 0.11 divided by 365 raised to 365 times 10. So this is going to be approximately equal to $12,014.67. And let's look at compounded continuously. So if it's continuously compounded, that will be this formula right here. And so let's see what the difference is. So notice there's a little bit more difference here. So now we're up to about a $2 difference. And the further along in time you go, the more this difference is going to engulf. So eventually that you would definitely make more money doing this continuously versus doing it every day. And that's kind of the point of this problem. So that's the end of this video. So up next we're going to talk about exponential growth and decay. See you then.